Hello dear students, this is Professor Anindya Das from Achievers and welcome to my lecture series on the second law of thermodynamics. So in our previous lecture we were discussing about the concepts of Carnot cycle and we have successfully determined an expression for eta reversible and we found eta reversible to be equal to 1 minus Tc by Th. Now in today's lecture we'll be using the Carnot cycle once again to develop the concept of a very important state function in thermodynamics, and that is nothing but entropy. So we'll develop entropy from Carnot cycle. So let's get into the. So what we'll be doing? Development of entropy from Carnot cycle. Okay, so we'll get into this. We'll develop entropy from the concept of Carnot cycle. So at first, let us draw the diagram of Carnot cycle once again. So what I have got? I have got two isotherms and two adiabates intersecting each other. So this is state 1, this is state 2, this is state 3, this is state 4, and you have successfully connected them. This is 1, this is 2, this is 3, and this is 4. Okay. And we also know that this is isotherm TH and this is isotherm TC. One is reversible isothermal process, 2 is reversible adiabatic process, 3 is reversible isothermal process, 4 is reversible adiabatic process. We all know these things. I'll not write it once again. I have already written it in details in our previous lecture. So I'm not writing it once again. Okay, that will be a redundant job to do. So our objective in the present lecture is to develop the concept of entropy right from Carnot cycle. So we'll be starting from the first law of thermodynamics. So what do we know from the first law of thermodynamics? From the first law of thermodynamics, we know that d cut q is equal to du plus pdv. Okay, when there is no non-mechanical work. When there is no non-mechanical work, so let us consider the non-mechanical work d cut w dash to be equal to 0. So not considering any non-mechanical work. So in the absence of any non-mechanical work, the expression is like this. Now for the present case, that is the Carnot cycle over here, this is a reversible cycle. So we can replace d cut q by d cut q reversible. What is our working substance? Our working substance is ideal gas, and for ideal gas we know that du is equal to cv dt. Okay. And again, for an ideal gas, we can write P to be equal to nRT by V. Done. Now let us divide each terms by t. Let us divide each term by t. Let us divide each term by t. So, getting d cut q reversible divided by t to be equal to Cv dt by t plus nr by v multiplied by dv, nr dv by v. T will get cancelled out. Now let us integrate both sides over the entire cycle, over this entire cycle. So let us integrate both sides over the entire cycle. Let us consider Cv to be independent of temperature. Let us consider Cv to be independent of temperature. If Cv is independent of temperature, then this Cv can be dragged out of the integration. So I have dragged Cv out of the integration. So I am getting Cv integral dt by t. nr is again dragged out of the integral because it's a constant. So I am getting cyclic integral of dv by v. Now students, t is a state function. If t is a state function, then cyclic integral of dt by t or cyclic integral of dl and t, dt by t is dl and t, cyclic integral of dl and t is 0. So this term must be 0 since t is a state function. Similarly, as v is a state function, so cyclic integral of dv by v or cyclic integral of dl and v, dv by v is dl and v, cyclic integral of dl and v is again equal to 0. Why is it happening so? It is happening so because t and v, they are state functions. So, naturally, the left hand side is reduced to 0. Therefore, you have got d cut q reversible by t integrated over the entire cycle is equal to 0. Now students, q reversible is a path function. Heat is a path function. But d cut q reversible by t, d cut q reversible by t is developing a sense of state function. Why? Because cyclic integral of d cut q by t, d cut q reversible by t is reduced to 0. Q is itself a path function. Heat is itself a path function, but this particular form, basically it depicts the meaning of a state function because this is the property of a state function. Cyclic integral of, if cyclic integral of dx is 0, then x is a state function. So you can replace this by ds. So I've written let ds is equal to d cut q reversible by t. Then one can write cyclic integral of d cut q reversible by t, which is nothing but cyclic integral of ds, this is 0. If we replace d cut q reversible by t by ds, then what we can say? We can say cyclic integral of d cut q reversible by t, that is nothing but cyclic integral of ds, that is equal to 0. That is equal to 0. Cyclic integral of ds is equal to 0. So from here one can say that S is a state function. From here one can say that S is a state function. S is a state function. So from here one can say that S is a state function. Okay. So we have got ds to be equal to d cut q reversible by t. We have got cyclic integral of ds equal to cyclic integral of d cut q reversible by t to be equal to 0. So from here, one can say S is a state function. Next, one can say that the dimension of S is basically energy divided by temperature. Energy is ml square T2 inverse, temperature inverse. Small t is time, capital T is temperature. But in order to get the actual significance of S, we must know statistical thermodynamics. Right now we are not acquainted with statistical thermodynamics. We just come to know from these facts that S is a state function and it has a dimension energy per unit Kelvin. It has got a dimension energy per unit Kelvin. You have got that. But the actual interpretation of S, the actual interpretation of S, which is known as entropy, the actual interpretation of S, which is known as entropy, cannot be made from the second law of thermodynamics. For that you need to study the statistical mechanics. But right now we'll not get into statistical mechanics. We'll just pin down the significance of entropy over here, but that will be revealed when we'll study statistical mechanics or the third law of thermodynamics. It will be revealed from the third law of thermodynamics. But now I am not going to get into the third law of thermodynamics. We'll be sticking to the second law of thermodynamics solely. So here entropy is a state function. Its dimension is energy per unit Kelvin, and it's a measure of degree of disorderness of a system. Although this cannot be explained from the second law of thermodynamics, from this equation we cannot explain it. From this equation we cannot explain it. But for the time being, we'll consider this particular significance of S, because in order to understand this significance of S, we must be acquainted with the third law of thermodynamics. Okay. So this is the significance of S. This is the significance of S, and this S is nothing but entropy. This S is nothing but entropy. So let us get back to the Carnot cycle once again. So for the Carnot cycle, cyclic integral of d cut q reversible by t, this cycle is comprised of 4 steps. It is comprised of 4 steps. First one is step 1, connecting states 1 and 2. Second one is step 2, connecting states 2 and 3. The next one is step 3, connecting states 3 and 4. And the final one is step 4. Final one is step 4. Connecting states 4 and 1. This entire thing is equal to 0. We have broken the cyclic integral into 4 terms. The first term comprises step 1. This term comprises step 1, which connects states 1 and 2. This term comprises step 2, which connects the states 2 and 3. The third term comprises step 3, which connects the states 3 and 4. And finally, the fourth term depicts step 4, which connects the states 4 and 1. And this entire thing is equal to 0. Now we all know that step 2 and step 4 are adiabatic in nature. If they are adiabatic in nature, then d cut q reversible is 0. Here also d cut q reversible is 0. So this entire term is 0. Here also this entire term is 0. Because they are adiabatic in nature. And what about 1 and 3? Step 1 is isothermal. If it is isothermal, then temperature is constant. So this 1 by T will be dragged out as 1 by TH. Because temperature is constant at TH. For step 1, temperature is constant at TH. So this T will be dragged out, and outside the integral you will have 1 by TH. Similarly, here also the temperature will be dragged out because it's yet again an isothermal process. And for step 3, the temperature is Tc, so you'll have a 1 by Tc term outside. So what do you have got? You have got 1 by Th multiplied by Q1. For step 1, the temperature is, for step 1, heat is Q1. Plus 2 is 0. Let's move on to 3. Again, you have got 1 by Tc outside. For step 3, Q is Q3. Again, for step 4, it's 0. So you omit step 4. And you have got this entire thing to be equal to 0. So what you have got? You have got Q1 by Th plus Q3 by Tc to be equal to 0. Now from our previous calculations, we know that Q1 is positive, so Q1 is QH. And Q3 is negative, so Q3 is QC. We know these things. So we already know that Q1 is equal to QH is equal to mod QH. This is positive. And Q3 is equal to QC is equal to minus mod QC. This is negative. So if we replace Q1 by mod QH, then you have got mod QH by TH. And if we replace Q3 by minus mod QC, then you have got minus mod QC by TC. This is equal to 0. So what you have got? You have got mod QH by TH to be equal to mod QC by TC. And mod QC by mod QH to be equal to TC by TH. By simple algebra we can write it. So eta reversible. Here eta is eta reversible. Eta reversible is equivalent to eta. By definition, the general form of eta is 1 minus mod QC by mod QH. And here we know that mod QC by mod QH is TC by TH. So it's 1 minus TC by TH. See, you can derive the expression of eta reversible in a different way from the concept of entropy. We have already developed the expression of eta reversible from the Carnot cycle by applying first law of thermodynamics directly to each and every steps. That was the conventional process of the determination of expression of eta. That's what we have done in our previous lecture. In the current lecture, what I have done, I have developed the concept of entropy out of the Carnot cycle, and from there I have manipulated the calculation in such a manner so that we can again derive the expression of eta. And naturally the expression remains all the same. Eta reversible is 1 minus Tc by Th. So I've got it. I've got it. Okay. Now I have a question. The question is, you see, eta reversible is equal to 1 minus Tc by Th. Now, you can increase eta by two different ways. If you increase Th, this is number one. If you increase Th, then Tc by Th will decrease, and there is a negative sign in front, so eta reversible will increase. And there is another way, you can decrease Tc. You can decrease Tc. If you decrease Tc, then Tc by Th will decrease, there is a negative sign in front, so again eta reversible will increase. For this process, you keep Tc constant, and for this process, you keep Th constant. So I have got two options to increase eta. This is option 1, this is option 2. My question is, which is a better option? Which is a better option to increase eta reversible? Which is a better option to increase eta reversible? Which one is the better option? Which one is the better option to increase eta reversible? How can we do that? How can we do that? Have you got any idea? Very simply, see, for option 1, the rate is given by R1. What is the rate here? The rate is the rate of change of eta with respect to Th. Rate of change of eta with respect to Th. What should be the value? If we differentiate with respect to Th, then the first term is 1, it's 0, minus Tc by Th, here Tc is constant. So what will happen? If we differentiate minus Tc by Th with respect to Th, then it will become Tc by Th square. Tc is constant, so it becomes Tc by Th square. This is positive. So R1 is equal to mod of R1 is equal to Tc by Th square. Now R2. What is the expression of R2? R2 is rate of change of eta with Tc. At constant Th. Now if you differentiate with respect to Tc, then what you are getting? Th is constant. 1 is 0, so you have minus sign. 1 by Th goes out of the differentiation. And if you differentiate Tc by Tc, you will get 1. So it becomes minus 1 by Th. It's a negative. So mod of R2 is minus R2 is equal to 1 by Th. Fine. Then let us take the ratio mod R2 by mod R1. Mod R2 is 1 by Th. Mod R1 is Tc by Th square. It is in the denominator, so the fraction will be reversed. It will become Th square by Tc. This Th will get cancelled out, so it becomes Th by Tc. As Th is greater than Tc, so Th by Tc is greater than 1. Therefore, R2 by R1 is greater than 1. Therefore, R2 is greater than R1. It implies that the second option is better. 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 So the second option is better. Second option is better. The second option is better. Understood? A very simple question. Okay. So this is all about the lecture where we have developed the concept of entropy and we have dealt with some interesting examples over here and some manipulations in terms of calculations. Okay. So bye bye for now.